Hello and welcome to the SKF webinar where we'd like to talk to you about managing lubrication in the food and beverage industry. It's said that the 7 most expensive words in business are "we've always done it this way," and we feel that this can be applied to lubrication and relubrication within the food and beverage industry. We see the need for people to consider over-lubricating, increasingly relubricating machinery and assets, and this is largely due to the contaminating nature of the processes themselves, and in particular with regard to the cleaning, the high pressure rinses and the chemical cleaning for hygienic purposes that goes on within the food and beverage industry. This leads to what we would consider to be endemic over-lubrication. So let's discuss the importance and the impact of lubrication. First of all, if we look at a typical maintenance budget, it's said that between only 1 and 3% of that budget is taken up by lubricants themselves. However, this can have, and the Lubrication Act itself can have, a very profound impact on company key performance indicators and on costs. It will impact output, it will impact on cost, and it will impact on compliance. If we look at just one of these facets in a little more detail, that is of cost, the companies that we work with, both globally and locally, tell us that probably between 15 and 20% of the typical maintenance budget can be impacted by lubrication and by poor lubrication practice. So let's look at this in a little more detail. What are the challenges? Why is lubrication such a big issue? And that is really around the environments that we see within food and beverage production. So first of all, the cleaning that is necessary for hygienic purposes. So this involves high pressure rinsing, the application of penetrative chemicals, which are actually solvents in nature, quite often to dissolve fats, but that means they also impact on lubricants as well. The application of heat in many of the processes. These can be temperatures sort of 180, 230 degrees centigrade in some cases, way beyond normal sort of grease technology. So this has a big impact on the relubrication process, the amount of relubrication that is being conducted. Even cold areas where we remove heat, so freezing applications, for example, can have a big impact on the lubricant within a bearing, the need to relubricate, and the performance of the bearing itself. And providing all of these environments are, of course, overall contaminating environments from the nature of the elements being used in the food manufacturing process. So what is the best lubrication strategy? We look at it in 3 elements. First of all, we consider, is it possible by the use of the correct technologies to completely eliminate the need to relubricate bearings within rotating equipment? If we still need to relubricate after that consideration, how do we minimise the amount of relubrication that's going on and the volume of lubricant that's used during that relubrication process? And finally, how can we optimise the relubrication process? How do we make it safe for people, for the environment, and for the product that's actually being manufactured? So let's consider each of these in turn. First of all, eliminate. We would say to customers we want to consider whether we can eliminate the need to relubricate, for example, ball bearing units on your conveyors. And the response quite often is people look at you with panic in their eyes because they see how unclean the nature of the application is, how aggressive the cleaning involved in the hygienic processes are, and I say we have to re-grease the bearings. At least after a hygiene clean, we need to replenish the lubricant in the bearing because we know it will be impacted by the cleaning process. So the washdown cycle in itself is often the root cause of over-lubrication. And it's a bit of a cycle, and it's very, very difficult to see how you can break out of that cycle. It's obviously necessary to hygienically clean manufacturing assets within the food and beverage industry. This is done by high pressure rinses, by the application of penetrative detergent solutions, and then for high pressure rinsing. Because of that, people are often relubricating, as we would call it relubricating to purge. So they're pumping grease into the bearing till the old dirty grease and even water that's got into the bearing is pushed back out of the bearing. That in itself is a contaminating process. The process material itself, as already discussed, so the actual elements that have been used in food production are contaminants in their own right. Because of the grease, because of the process material, cleaning becomes ever more needed, can become ever more aggressive. So we see the impacts of detergent water ingress. So we relubricate more frequently. So you can begin to see the picture here. That it's a bit of a cycle, and the question is, how do we break out of that cycle? How do we eliminate relubrication despite the hygienic cleaning, despite the penetrative nature of the fluids that are used, and despite the high pressure washdown? So at this point, I'd like to hand over to my colleague, Fabio Falaschi. Fabio is very involved in the development of many of our food and beverage dedicated products, and he wants to go into much more detail about the mechanics in terms of how this the process of these contaminants getting into the bearing, how conventional sealing might be impacted by this, and then how sealing might be developed to better accommodate this contamination. So I'll hand you over to Fabio for the next few slides.
Hello everyone, my name is Fabio Falaschi. I'm the Product Development Manager for Ball Bearing Unit in SKF. And today I want to talk about IP69. Is it really a safeguard? IP69 is a very well-known and recognized certification on the market. And in fact, we hear a number of customers asking about IP69 rating certification. Well, I'd like to bring you some insight from our test. So, first of all, let's take a pretty high-end bearing IP69 certified. Let's take also the test that we call the detergent droplet test that we in SKF developed to try to replicate as much as possible what it happens actually on the field when it comes to washing down with the detergents. How this test is working? Yeah, you see a little needle here, and this needle is supposed to let some detergent mixed with water dropping into the bearing to see what happens to the bearing itself after this contamination. So we have some 1000 RPM speed because this is an accelerated test for a pretty long time, 500 hours. And then we want to check the status of each component after this test. Okay, so let's see together. One by one, let's see the sealing. The sealing is very deformed, as you can see here, not really close, unfortunately, to the nice shape shown in the picture. And then we have these inner ring grooves here. And these grooves are made by these two contacting lips. Well, here, the first time I've seen this phenomena happening, I was like, wow. I mean, I could not really believe that basically the rubber is able to machine hardened stainless steel. This is really incredible. But we have seen this over and over and over again. Both in the field and in our test, and this is really what it happens when the lubrication in this area fails. Then what else? We have the sealing system here, which has one lip completely detached, and the reason for that is that the detergent is so aggressive that dissolves the bonding agent between the metallic shield and the rubber. And also, one lip is completely lost. I have no idea what happened here, but something really tough and strange for the sealing system. Then we have the outer the raceway here with the measure indentation, measure indentation, as you can see here. And I tell you, when you have indentation like this, the bearing life is not really much. There's not really much remaining in bearing life here. And finally, the grease, which was originally white, is very oxidized, and you don't really want this kind of grease inside your bearing. Okay, so what we can say here, we can say that the AP69 rating at the best is a safeguard against water. It's not a safeguard against detergent. Detergents are very aggressive and they trigger a completely different failure mode for the bearings. So think about this. What the detergent is supposed to do, what it's designed to do, is designed to wash down fats. And, the grease, when it comes in contact with the detergent does what is designed to do. And so take the fat part, which is the oil, and separate the fatty part from the thickener. Now, when this happens, unfortunately, the thickener is there for a reason. It's there to keep the oil part of the grease inside the bearing. So basically, this detergent will wash down the oil part of the grease, and you will have the bearing just with a thickener. But the thickener has no lubrication properties at all. So you will have a dry running, and the grease, it's not even a grease anymore, it's just the thickener, will be completely compromised. And this is what will happen with this, again, these grooves that we've seen also before, and this bearing, which is completely destroyed. And I think the picture is really speaking by itself here. So we can absolutely state that an effective grease technology should withstand the effect of the detergent. And then let's see also, let's speak about sealing technology. And let's take this solution with two contacting lips here, one axial and one radial. And here we have a drop of detergent mixed with water. Now, the detergent is designed not only to wash down fat, but it's also designed to go through everything. And this is the reason why the detergent has such a low surface tension. This low surface tension is the reason why you cannot in any way avoid this detergent to go through your contacting lips. No matter how many you put, sooner or later, much sooner than later, in my experience, the detergent will go through. So let's see what happens. So when this is coming through the sealing system, it will get in contact with the grease. And we have seen before, the phenomena here is that you will have the thickener and the oil, which will be separated. And you will have this sealing lip running dry. This will increase the friction, will increase the temperature, will increase the wear of the sealing lip. The only thing that will be decreased will be the barrier life. So usually, what is the standard perceived solution or fixing for this is you take your pump and you pump fresh new grease here. So doing that, you basically pump out the exhausted grease and you have fresh new grease here. Fine? Not really, because doing that, apart from any consideration on hygienic design, food safety, and cost also in doing this, but there is also another aspect. Let's see what it happens inside. Here you will have an extreme pressure because this pumping procedure creates this extreme pressure here, and there's no way that after the procedure is over, you can assess if this lip is still working properly, it has been damaged, or you just cross the finger and say, let's hope that this will work. Is it really the best solution that we can have here? Well, let's have a look to this. This is our SKF patented gutter sealing system. And we knew, I told you that there is no way that you can avoid this detergent to go inside because it's designed to do that, you know. When you cannot actually avoid it, we say, okay, as they say, if you cannot beat them, then join them. So let's try to use the same characteristic that is annoying, so the low surface tension, and we take advantage from this. Okay, so let's have a look at this animation. So this is the section of our gutter sealing system. And let's suppose that you wash down with high pressure water and detergent as you do on the field. And the majority of this will be kept outside the bearing, but some drop will go inside. And we know that, we knew since the beginning when we designed this. But what it happens, this will be collected by these gutters. As it happens, it happening in your house with the rain, and the gutter collecting the rain. This is the same concept. And thanks to the low surface tension, this will be easily driven on the outside of the bearing, either by gravity, or if the bearing is rotating, even better, thanks to the centrifugal effect. So, develop innovative technologies that work with the prevailing water and detergent mixes applied, as opposed to those that just try to fight them. If you know you cannot win, you shouldn't even play that game. And here it's the same. If you cannot avoid that the detergent is coming inside your bearing through any contacting lip you can have, then you should not even have that contacting lip, and you should approach in a different way. And this is what we did. So let's have a look about this. This is a washing down procedure from the front of the bearing, and this is a real picture coming from the field about what is inside one of the cover. After you wash down, I think everything is cleaned and shining. And this is really, scaring when it comes to food safety. And pretty the same is happening from the back side. When you have flanged unit like this, you have this through hole for the shaft, and everything can go through. And I want also to talk about this. This is the so-called standoff solution, in which you basically separate the bearing unit from the frame. I want to share with you this. We made an independent washdown test by microbiology and hygiene expert at RISE, RISE, Research Institute of Sweden, who compared the cleanability of standoff with the ones mounted on the frame with the base seal solution. I advise you to watch it yourself on YouTube. But anyway, the conclusion is that the food residues are still present. We can see here, if you zoom, these are food residues. And well, can you clean them? Yeah, maybe yes. Maybe you can do better than this, but in the real world, when you have to put attention in this when everything else looks fine, and do we really want to take this risk? Is it really the best solution possible? So grease from the front and from the back is an important consideration, as well as food residues. And this is what we developed in SKF, a solution which is sealed from the front side, thanks to this innovative and reliable anchorage and sealing implemented in our end cover. and also the combination of the base seal solution, which is a unique feature on the market worldwide, together with our back seal, and this is the same situation as before, create this this very, very effective sealing from both the front and the back of the unit. So thank you very much for your attention.
So thank you, Fabio. I'm sure you will agree. Fascinating insights there from Fabio. So moving on, just quickly touching upon the need to keep the lubricant within the bearing and from a sealing perspective, keeping cleaning and processing contaminants out. Sealing materials should really be able to withstand the operating conditions. So the materials, the design itself should be optimized. So if there are particular requirements for the seal, it should be built into the design, whether that may be something like lip profiles, ability to withstand certain environments, etc. And customized solutions. I mean, if we're able to customize solutions, build the sealing component, for example, into a plastic holding element, a customized solution can often work better than one that is defined by the original equipment manufacturer. And we frequently work with end users to develop and manufacture and apply high efficiency external sealing. So eliminate relubrication despite pressure wash. We've touched on this already. With the right sealing and with the right lubrication technology, with the right sealability of the insert bearing, that's the bearing unit itself and the sealing surrounding the bearing, you can improve reliability. You can significantly improve reliability quite often. That will reduce the amount of bearing units that are being changed and reduce the amount of time that's taken to change them. Net result of that is better availability, more production. You can eliminate the need to relubricate. That's saving maintenance time and cost, an overall cost reduction from the maintenance budget. You can reduce the effect of grease in the wastewater stream, for example. So that means that there is less impact on the environment. And you can most certainly improve food safety. So because there is less excess lubricant in and around the bearing, there is less risk of the contamination of the food product. And in these days of ever increasing food recalls caused by contamination and the risk to the business from a reputation or cost perspective, then obviously protecting food safety is paramount for many of our customers in the food and beverage production industry. How do we eliminate, or let's consider eliminating the need to relubricate in high temperature areas? As already said, when we're looking at temperatures, maybe 180 degrees C is a sort of a mid-temperature that we often see. It's really at the top end of the capable operating temperature of many greases, and therefore people tend to want to relubricate or replenish those greases much more frequently, and they are expensive in themselves as well. So when we look at such applications, and the image that you can see here is a wafer oven production unit for the confectionery industry in this instance, and when we go and see a customer like this, we might well be told by them that actually we're quite happy, you know, that we have a relatively reliable process, that we manage to achieve the efficiencies that we expect to achieve. You know, we don't really feel that we have any problems. But when you start to look at the application in more detail, to begin to understand the process, understand that there's a lot of oxidation going on, that there's a lot of maintenance activities of various kinds needed to achieve this reliability, then you can begin to understand that in order to get reliability, there is frequent and very expensive maintenance going on, that there is a lot of planned and a little bit of unplanned downtime that is being incurred, and there is a limit to the ability to change production. The grease technology in itself means that you can't get to higher temperatures. Therefore, you can't perhaps increase the speed of the oven and increase the temperature to achieve the same result and increase production. It is a bar to being able to do that. So we very often and frequently move to look to graphite technology for our bearings in high temperature applications. The ability of the bearings having, for example, a graphite cage, the graphite being a sacrificial lubricant, it wears very, very slowly through the life of the bearing, actually would enable process temperatures of up to 350 degrees centigrade. Obviously, we really don't see those temperatures in food production. As said already in the preceding slide, maybe sort of 230, maybe even 240 degrees C. But at those temperatures, these bearings will run quite happily and without problem and give a long, reliable life. So by applying this technology, you can eliminate the need to re-lubricate even at very elevated temperatures. So there is a significant saving in terms of the cost of the high temperature grease in itself and a reduction in the maintenance downtime needed to either re-lubricate bearings or to change bearings. So that has a net impact of less cost from the maintenance budget. You can significantly improve reliability, thereby less planned activity, less planned maintenance, more availability of the production equipment. You have the potential to increase throughput. You can increase operating temperatures. You can potentially increase the speed of the oven. So that would lead to higher production, better profitability. And you will improve operator safety. There's less maintenance required. There's less invasive maintenance to do on potentially hot equipment. So this will have an impact on operator safety as well. A number of benefits here. Overall, high temperature areas, please consider graphite-based lubrication technology, particularly in deep groove ball bearings or even bespoke designed units. So low temperature applications, moist areas. This is quite a difficult area, and we'll have a few videos here which will hopefully illustrate this to you. So the image to the left shows a freezer application, a hardening tunnel in the ice cream industry maybe, or a tunnel or a freezer for freezing desserts, cake and such like. And in these we see a large sprocket moving the chain to move the product around the freezing system. And at the center of these is a hub, typically containing two bearings. So I'll show you a quick animation here. When a hygiene clean goes on, a higher temperature water is brought into the freezer to begin the cleaning process. So temperatures of maybe minus 40 degrees centigrade will start to increase and will increase relatively quickly. So as the warm water starts to be applied in the cleaning process, the temperature will change from minus 40 to maybe plus 25, plus 30 degrees centigrade. There's a lot of air in the grease in the bearings that expands. Then once the cleaning has been done, the freezer is plunged back down to temperature very quickly. So the temperature goes from maybe plus 20, plus 30, down to maybe minus 40. And the moist air is sucked back into the bearing. That's something called breathing. And within a bearing, it will lead to corrosion, the risk of grease contamination, the potential emulsification of the grease, and in some cases, even ring fractures in bearings, most definitely impacting on reliability. The other issue as well, if you look to the animation to the right-hand side here, is that during this process, small amounts of lubricant are potentially released. Because of the blast from the freezing air being moved, they spread around the freezer, drop onto product, causing something called black spot. So the grease emulsification, the breakdown of the grease, it escaping from the bearing results in contamination of the product, and it's quite often described in this way as a black spot. So how do we therefore eliminate potentially the need to relubricate in these low temperature and contaminating areas, given that we see the emulsification of the grease with water? We quite often apply alternative lubricant technologies to such applications, and illustrated here is an SKF development which is called solid oil. So solid oil, as opposed to a conventional grease, is a polymer which is saturated in oil, and as it releases the oil, that acts as the lubricant. So if you look at the image to the left-hand side here, the first test tube would show you a typical grease, and within that typical grease there's a lot of air. There's a thickener which holds the oil, as described by Fabio previously, but the oil content is only about 35% of the total volume, and that is the amount of lubrication that's available for the bearing. If we look at solid oil, which is the test tube to the right, the holding matrix is polymer, and because there's no air in there, there's about 70% of that volume is filled by oil. So more than twice the amount of oil is available as a lubricant with solid oil compared to grease. So solid oil is an oil-saturated polymer material that virtually fills all of the free space within the bearing. It doesn't emulsify in the presence of water. It's resistant to most chemicals, it's chemically inert, and it enables effective minimum quantity lubrication. There is more oil available to lubricate the bearing than if you had a grease-filled unit. So therefore you can reduce planned and unplanned downtime, and therefore maintenance cost. That takes excess cost out of a maintenance budget. You can improve reliability, which reduces the effect of cleaning and the processing environments, and again, improving availability of assets. You can improve operator safety, so there's less risk. If any of you have ever worked in a freezer environment and had to go into a freezer at very low temperatures, you'll know that it's a very uncomfortable process, and certainly you wouldn't want to be going in there too quickly to do any maintenance. So there are safety issues involved. And there's a reduced waste of grease and clean-up in terms of disposal of that grease, which is much better for the environment as well. So in conclusion, low temperature and contaminated environments, consider solid oil, consider a low temperature, food grade, solid oil based lubrication technology. The next thing that I'd like to discuss with you is minimizing lubrication. So we've talked already about the over-lubrication issue within the food and beverage industry, the grease to purge, and we've talked a little bit about how we might eliminate the need to re-lubricate. But obviously there are applications where we do still have to re-lubricate bearings. So how might it be possible to reduce the amount of lubricant potentially that we apply to the bearing, and how might it be possible potentially to reduce the number of times that we re-lubricate a bearing? So first of all, over-lubrication. We've talked about greasing to purge, we've talked about over-lubrication, and this is prevalent and endemic even within the food and beverage industry. We believe that over 75% of all bearings and chains and such applications are over-lubricated, and that's in the belief, the mistaken belief, that this safeguards reliability, when the reality is that it actually decreases reliability. It actually introduces many more problems than it solves. So we see in wet production areas, people greasing to purge, to push the excess grease, the dirty grease, the water, the product back out of the bearing. In high temperature areas, we see people feeling the need to re-lubricate very frequently because the grease is aging prematurely. And even in packaging areas, we see people feeling the need to grease and to over-lubricate as well. So, in minimising lubrication, people ask, well, actually, what is wrong with putting a little bit of extra grease into a bearing? What is wrong with re-lubricating bearing, more frequently than perhaps it requires? Extra grease in the bearing can only do the bearing good. Well, the reality is that it, without doubt, puts reliability at risk. Food safety, because of excess grease, because of leaking grease, could definitely be compromised, And operator safety can be at risk because there's an increased need for maintenance, more people on or around the machine trying to access grease replenishment points. And overall, it is an unnecessary cost. So it has an impact on the maintenance budget as well. And if it can be reduced, it can take that away from the pressures and the stresses and strains on a typical maintenance budget. So how do we do it differently? Well, we work with many customers with regard to try and minimise the lubrication, minimise the re-lubrication process. This would start with a review of the current planned maintenance activities around lubrication. For example, sometimes that might just be the operator greasing as he sees it at need at the machine, or it might be a planned maintenance activity whereby at set intervals you're going to the machine and re-lubricating with a set amount of lubricant. So we would be talking to customers about beginning an incremental reduction of lubricant use. That, of course, under strict condition-based monitoring. So that could be vibration analysis, that could be visual analysis, that could be grease condition analysis. But under those conditions and understanding those conditions, we incrementally reduce the amount of grease and incrementally reduce the frequency of the re-lubrication process. And through this practice, we would typically see an average of 20 to 50% less lubricant used in such instances. Optimizing lubrication. So this is really where we consider how best to deliver lubricant to the bearing. We've already talked about reducing the amount of lubricant, reducing the frequency of re-lubrication. But the reality is the best way to lubricate a bearing is little and often. But that just isn't practical if you're doing it manually. So how else can we consider lubrication optimization? Well, to begin with, we need to understand the requirements of the lubricant. We need to select the right lubricant for a typical operating condition. We then need to identify the best way, the right way to deliver that minimal quantity, very small amount of quantity, much more frequently. We need to consider the application of this technology. We need to consider the cost of introducing that technology and the potential risk to food safety in using that delivery method. So we need to measure, we need to understand, we need to learn, and then optimize how we're delivering lubricant and how we can improve the frequency of delivery of very small amounts of the lubricant. So one of the ways that we do this is by considering a process of understanding the needs of the lubricant, how to deliver the lubricant, if we're operating and lubricating manually, how we deliver the lubricant, how often, how much, have the knowledge and right skills to do this. So training is a big part of this as well, because what we tend to see, if people are lubricating manually, they don't really understand how lubrication is used. So there's a really big lack of understanding of lubrication in itself, which leads to bad practice when lubricating manually. If we do have to re-lubricate, consider trying to automate the re-lubrication process. This enables us to deliver the lubricant in the best way, which is little and often. And as we've already talked about, consider the many re-lubrication-free technologies which are available to you today. So Fabio has talked to you at length about the sealing technology that we incorporate into our ball bearing units. I've talked to you about high temperature applications and how the use of graphite can take away the need to re-lubricate. We've talked about maybe low temperature applications with a low temperature food grade solid oil which doesn't emulsify in the presence of water, has a large reservoir of oil which enables you to lubricate the bearing over longer periods. Maybe re-lubrication free chain in such applications as well. And finally, high efficiency seals. Let's protect the inside of the bearing. There's a lot of capability out there. There's a lot of ability to to manufacture seals, to machine seals from thermoplastics, to manufacture them to a set design, to a set size, but specially select the material, specially select the lip profiles to give you the maximum efficiency for sealing in and around the bearing. So let's manage lubrication. Let's consider this and put a strategy in place, looking at how we might manually lubricate the bearing, how we might automate that lubrication, how we might eliminate relubrication completely, and how we can seal away the contaminants from the outside of the bearing and keep the lubricant in. So managing lubrication as a strategy, instead of just going out there and saying, relubricate this bearing after 2 weeks with X number of grams of grease. So now you may be asking, well, how do we deploy this? How do we bring all of this together? Well, we conduct many what we call technical assessments with our customers. So this involves a very detailed line walk with somebody who has good knowledge of maintenance practice and the operation of a particular asset or a particular line. So standing by the machine, talking to that particular person, we can identify solutions to issues as they're reported to us, as they're seen by us. We can identify simple fixes and quick gains. We can see and identify and report opportunities for the potential technology upgrades. We can then support that with references from similar applications where we've had successes previously, and sort of support in enabling a move to perhaps a more preventative, maybe condition-based maintenance strategy as well. This is an example of a customer of SKF's, a potato processor, and how with SKF's help he redefined his lubrication management. He was in need of a line that was completely reliable during the potato season. He wanted to try and better understand how well his current lubrication program was supporting the reliability of the assets, how it was impacting on cost and impacting on safety of the team operating the machines and maintaining the machines. So SKF conducted a lubrication assessment on site. The SKF team observed that whilst lubrication routines were rigorously followed, manual lubrication was time consuming. There were issues with tools and storage and cleanliness, so that needed a bit of a lift, and there was clear evidence of excess bearing grease from over lubrication on lines, and that was identified as a likely food safety risk. So together, SKF and the customer developed an improved lubrication management proposal that enabled the customer to significantly save on the maintenance requirements and the costs associated by the application of an automated or more automated lubrication process. It reduced the potential food safety risks and it improved reliability. And through root cause analysis, we were able to identify the best fit grease for critical application conditions and sort of bridge the knowledge gaps of maintenance staff with training as well. So this is just a simple case study of how we could significantly improve the situation with the customer in terms of lubrication manage and deliver some good savings to the customer, as well as improving reliability at the same time. After that was put in place, the customer and SKF agreed that by paying a monthly fee for the full reliability service during the production season, then he was able to realise multiple benefits from the expertise at SKF and by adopting the proposed improvements in the maintenance strategy. So, what is the journey towards performance? What does it look like? Well, it starts with increasing the mean time between failure by the application of technology, by providing design upgrades in machinery, understanding what is required and how to deploy that. Then maybe moving to consider more asset performance, maybe look at predictive maintenance techniques to develop a good understanding of the root cause of failure and what technologies may be appropriate to mitigate or eliminate that, and maybe a maintenance strategy review based upon that asset, or maybe even the line. And then consider the very much bigger picture: plant output, availability of assets or availability of lines, that driven by key performance indicators, by focusing on planned and unplanned downtime reduction. Maybe as well as that, optimizing or looking at optimizing inventory and spare parts stock levels to support new maintenance strategies. And obviously, lubrication management can be a big part of that as well. So thank you on behalf of Fabio and I for joining us today. We hope sincerely that you found it interesting and you've got some good takeaways from what we've shared with you today. If you can give us any feedback, we'd be absolutely delighted to receive it. Please, in chat, put some comments, tell us what you think about the material, what you think about what we've said to you today. And of course, if you have any questions, we'd be more than happy to address those for you as well. So once again, thank you very much for joining us today.